Hello and welcome to day 7 of the 2024 Advent of Code. Today we've got a puzzle all related to making numbers on the left out of the right hand ones. We're going to be using Python for this, and the problem this time is that we have these set of rows, and the task is to leaving the numbers the way they are in terms of ordering, and using all of them. If in these spaces you were to add pluses or times, is it possible to make the left-hand number? So example here, 190, if you had a times in the middle, would be 10 times 19, that works. If it was a plus, it wouldn't work, but we just need to find one way. Similarly here, if we had plus times, and also times plus works here. And the way that we evaluate these operations is always left to right, and it's not according to precedence rules. So, we don't do the multiplications first and that kind of thing. So here we would do 11 plus 6, then times that result by 16, and then add that result to 20, rather than what you might expect, the times first and then the adding. It's always left to right. And yeah, just to stress that it is just these numbers in this order, and it has to use all of them. So let's hop straight into VS Code. I've just loaded in here. This is what we've just seen on the web page. And what we're going to do is we're just going to make a list of reports. So let's say for each of these, we're going to get the parts of it by splitting on the column. And if I was to just print the parts just to show you what that looks like, something like this. And so we have one thing here, and then we've got a space and then all the numbers here. We're going to then take each of these and we want to make a tuple of this and then an array of these. One way we can do that is to take each part, take the 0th one, turn that into an integer. And for the second one, I found this nice trick where you can take the first parts, or this part, you could strip it to get rid of the white space on either side, or in this case just on the left side. Split it on space, and then we want to map each of these to be an integer. I always used to do this with, x for x in x's, and then something like that. But one nice, neat way to do it is to say map int, like this, and then to make a list of that. And then we're going to add this thing to the reports, or append it to the end. And then if I just print the reports, we'll get this. So we'll get 190 with these as the elements, 3,267 with these, and then we're going to go ahead and check each one. So we could say for the report in reports, let's take the target, which is going to be the left hand side, and the inputs as the right hand side. What would be good if we could get all possible equations, if I could spell, like that, by generating of this input. And so this means, for example, if we had the input of 10 and 5, we'd want to get 10 add 5, and then we'd want to get 10 times 5. And similarly, if it was a 4, we'd want to get plus and times in here and plus and times in here, so there'd be 8 different combinations. I believe, oh no, sorry, they'd just be 4 because of the, there's 2 spaces. And one nice way to do this is to think about all those spaces. So say if we took one of the longer ones here, you need, so there's 4 here, you need 3 operations, and we need 2 different ones for each one. So we need a plus or a times, and we need 2 to the n minus 1 of them, if n is the length of the array. But instead of pluses and I shouldn't do that, it's a little confusing. Instead of pluses and times, if we had zeros and ones, suddenly this starts to look like binary numbers. And what we can actually do is list them all out with all of the binary numbers of length n minus 1. And to give an example here, with these 3 numbers, if we had of length 2, so we had 0, 0, 0, 1, 1, 0, 1, 1, 1, this would correspond to, say, add multiply for this one, multiply add, and multiply multiply, and then we've got all of them, and so we can check all of them. So that's what the implementation of this is going to do, and then we need some way to evaluate that. So we could say for all the equations in all possible equations, if the target, which is this thing here, is equal to, we could say, evaluate this equation, then return, then we know that this report is possible. So we could add a counter, and we could make the counter go up 1. Later for part 2, we'll take this into a method because we'll need to use it, but for now, this is fine. Let's remove this, and let's implement these 2 things. So to start with, I'm going to implement the generating all equations for an array of inputs. And the way that I'm going to do that is to first get all of the binary numbers up to some amount. So I'm just going to say that for now. So binary numbers of, let's say, of length rather than of size. And we want this to be n minus 1, where n is the length of this. So we're going to use that. We're going to use another function for that, which actually we'll do now quickly. One way to do this is to say we want all of the numbers up to 2 to the n. So we want idx for idx in range of 2 to the n, because that's what we were describing down here. Remember, we had 4 things. We had 0, 0, 0, 1, 1, 0, 1, 1. Now these are just the representations of 0, 1, 2, 3. So there's 4 of them. So we need all the numbers up to 2 to the n, apart from the last one. And we would convert them into a binary number. And so the way that we would do that is to say bin of this, it's a built-in function. However, this appends 2 things to the start. There's 2 characters. So if we do that, we just chop them off, and that's what we want to return. But the one issue left with this is if we say, if I just comment this out for a second, of length, say 3, we're going to get things like this, 0, 1, rather than ones that are the full size. And remember, we want leading zeros because they represent pluses in the leftmost, groupings, in the leftmost pairings. And so the way that we can do that is with a function called zfill, which will left fill with zeros up until, makes it of size n. And so for us to do it now, we'll see all of these being size 3, but these still represent the same binary number. So back to here. When generating all the possible equations, we get all these possible binary numbers, and we want to create all the possible equations from that. And so the way that I'm going to do this is to say for binary number in all the binary numbers, we want to loop through it. And so we want to loop through, say, with 0, we want to take the first equation, first input, then the first binary number, then the next input and the next binary number, and etc. So we've got one of these binary numbers, and we could say for index in the range of the length of this binary number, or the length of the input, but let's do the length of the binary number. We're going to make a set of equations. So equations, we're going to say, here's the equation for this particular binary number, which we're going to have as a series of, it's going to be a array of numbers and operations. We'll say first that we want to add the first input, so let's add that. And then, depending on what the binary number index is, so remember this is going to be a 0 or 1. We want to say if the binary number at this position is equal to a 0, we want to call that add, an addition. So we'd want to next add a plus. So it's going to eventually look something like, 1 plus 10. And then we hope to also generate this, and then we're going to evaluate all of these. So similarly with the first one, we're going to add a star. And then what's going to happen is we're going to run through the length of the binary number. But if you remember, the binary number is all of the spaces in between. So we're going to miss out the very last input. And so at the end of this loop, we're then going to add the last input, which you can do like this. And then now we have this equation, we're just going to add it to our list of equations. Just like that. So that should generate all the possible equations for us, for some inputs. If we were to test that out, if I was to print all the possible equations for, say, 1, 2, and 3, we should get, see, there are 2 spaces, so we should get 4. Oh, let's test what's going on here. So inputs, a little typo, none. Because we've not actually returned the equations. So we've got 4 here, and you can see we've got adding, timesing the second one, timesing the first one, and timesing both of them. And so that is everything we expect from there. Now we want a way to evaluate them. So we've generated all of them, and now we want to evaluate all these. So we want to evaluate this to 6, we want to evaluate this to 3, 3 times 3 being 9, and so on. Let's make our evaluation function. And this takes in an equation. And the way that we're going to do this is to use what's called a DQ, or a double-ended Q. If you're not familiar with this, it's really similar to a list. So if you imagine a list, when you're appending things to the list, say I append something here, 10, I can pop this one and I can remove this last one really easily, and I can add things to the end of it. But adding and removing things to the beginning is difficult with a list. With a DQ, it has an implementation that you can add and remove from both sides, which is really nice because we want to be going from the left to the right rather than the right. If it was the right to the left, I'd just use a list because we can pop and we can add. And our strategy is going to be, we're going to take the 3 left elements, combine them, add it back into the equation, and then call evaluate again. And we're going to keep going until there's only one thing left. So let's use our base case first. If the length of our equation, which is going to be a DQ, so I'm actually going to call this DQ to remind us, if it is of length 1, then we can return the first element, or the 0th element, and we're just going to cast it to be an int, and we know it will be an int. One thing I'm just remembering here, that in fact here, when we're generating all the equations, we don't want to return a list, we want to return a DQ. And DQ is something that's brought in from collections here. Because if it was just a list, some of the operations that I want to do here wouldn't be available to us. So I want to take the leftmost element here, and the way that I do that is by saying my DQ here, or equation, and I'm going to pop left, which gets this one. I'm then going to do the same thing for the operator and for the second one. So now we'll have 1 plus 2 for here, and then I'm going to look to evaluate them. So if the operator is equal to a plus, then we're going to add the 2 together. So the result is going to be n1 plus n2. And then we're going to take our DQ, we're going to add it back to the left. So that's the equivalent of taking them off, these 3 off the left side, doing this evaluation, and then sticking it back on the left side. We're going to append the result, and then we're going to call the function again, or we're going to return the function again. DQ. And so this is going to have recursion. It's going to keep going until there's only 1 left, which would happen here after we remove these 3, add that on. Then we'd have 3 times 3, that would be 9. There'd only be 1 thing left, and then we'd return 9. It'd come all the way back up through the function calls, and it would return 9. And really similarly here with times, we would just times them together. So if we're to look again here, we've got the target and our inputs. Generate all the possible equations from that inputs using all the possible binary numbers of length n-1, where n is the length of the inputs. Then we're going to evaluate each of those equations, and if it's the same as the target number, then we know we can hit it. And there's no need then to test other ones, because we've already hit it. So we could then go on to the next report. Let me test this out first. So let's see what this looks like. I'm going to print out the counter. I think it's always good just to get a bit of a sanity check. So there is no pop left on DQ. So let's have a see here. My item is a list, which is not what I want. And I think what's happened is, if I go to evaluate, the equation itself is what I want to be a DQ, not the list of equations. That was the wrong way around. But the logic's still the same, the actual equation we want to be able to take from both sides. we actually need to take from the left side, and what I did was I flipped the equation and then just did it normally from right to left. I did it from right to left just using a normal array, but it actually complicates things in part 2. So we'll just do it like this. Let's run. We've got 4 here. What did we expect? We only expected 3. And the reason we've got 4 is because we've counted this one as 1. We've counted this one as 2. And we've counted this one as 1. So, we've sort of double counted this one. And what we want to do is just have 1 for each. So we could try to break out, continue to the next report. What I'm just going to do is to take attainable targets. I believe that's how you spell attainable. Set, and I'm just going to add the target to it. And then what I'm going to do is I'm going to sum up the attainable targets. And this will be fine for part 1. It's a relatively small and relatively quick. Later on we'll be pulling this into a function and it will be returning here, so there'll be no extra work done. Let's give this a go. So that's 3749 on our testing input, which is 3749. And if we do this now with the actual data rather than the test data, we get this large number here ending in 754, which is what the result is here. Okay, now moving on to part 2, and it's really similar to part 1 actually. In part 1 we had zeros and ones mapping to pluses and multipliers. Now we're going to have a new operation, this concatenate, which just sort of sticks them together. You see it removes the space in the middle. And we can have, rather than binary numbers with zeros and ones, we could have ternary numbers with zeros, ones and twos, and just map that in a really similar way. So whereas before we had something like, say if we had the inputs 4, 5 and 6, we would have 0, 0, 0, 1, 1, 0 and 1, 1 for, plus, plus, plus multiply, multiply plus and multiply, multiply in these two spaces. Now we'll have the option, one more option. So we would have something like this, 2, 0, 2, 1, 2, 2, where each of these 2's would map to concatenate. So we can generate all the ternary numbers similarly to how we did all the binary numbers, and then when we're evaluating, there's just a third option and we can just make the operation for that. So let's generate all of the ternary numbers, and we're going to use it here. I'll rename that in a second. Ternary numbers of length n. And it would be nice if there was something a little like this. So if I could just go, say, ternary, that's for the right. Ternary like that. But there's not one like this in Python, like in this kind of standard library. At least I don't think there is. There might be one in a library that you can import. So we'll make it ourselves. I'll show you a small little algorithm for that. And we'll need to go up to 3 to the n now rather than 2 to the n. And actually, we won't need to snip off the beginning bit, and I'll show you why. So I'm going to give you an example here of this. So just a number. I'll give you an example in base 2, so in binary, and then hopefully I can convince you that with changing one number, it's ternary. So say if we had the target in base 10, if we had a number in base 10, and that would be, let's say 10, and we wanted that to be in base 2, which is binary, that is 1010, and we need an algorithm to get from here to here. And what we do is we have our empty output here, which we're going to add to, and the algorithm goes like, you take the input, you do modulo 2, modulo the base, and that gives you, in this case, 0 because 10 is even. You take the input again and you do integer division on 2 again, the base, and in this case that would give us 5. And then we take this 0, and that's part of our output. It's the rightmost part of our output. And this 5 is the output of this round, this iteration of the algorithm. And then all we do is plug the 5 into the input, so where the 10 was. So here and here, 5 modulo 2, 2 stays the same because that's the base, and that's 1 in this case. 5 divided by 2 would be 2.5, but this is integer division, so it's rounding down, so that's 2. We take this 1 and we put it to the left of the output. Our output is 2, and we put it back in. 2 modulo 2 is 0, and 2 integer divided 2 is 1. We take this 0, put it to the left, put the 1 back in. 1 modulo 2 is 1, because 1 is odd. 1 integer divide 2 would be 0.5 rounded down, so 0. 1 here, and then when we hit 0 we stop, and you see here, this is the output we expected. And hopefully I can convince you here that actually if we change this to be any number, so 3 or 54, any number you want, that will be the base. So if we were to change this to be 3 in this algorithm, we'd get 10 in base 3. So let's do that algorithm. So let's have our output here, which is just an empty screen. I'm going to say while the number, because we're going to keep iterating on it, is more than 0, we're going to get the remainder part, which was that 3, and we want to add it onto the left side of this. So one way to do that would be to say output is the string remainder plus the output. That's going to add it to the left side. Then we want to integer divide this by 3. So we could write something like this, but the shorthand for this would be like that. And that's just going to loop and loop and loop until we hit the remainder being 0. Well, the number being 0, but you know, the remainder afterwards would be 0. And then we'd stop and we'd then return the output. And I'm sure there's more compact ways or, you know, fancier ways to write this. You could, you know, obviously put this in here, but that works for our case. And in the same way, it's going to fill up so that it's the right length all the way up to 3 to the n rather than 2 to the n this time, because there are that many possibilities. So here we're going to generate all of the ternary numbers. This is binary number here. Instead of binary number, I'm just going to put number just to be more general. It could be ternary number, and every time it sees a 2, it's going to add this new operation, which is the concatenate symbol, concatenate operation. And last thing, all we need to do is be able to recognize that operator, which is here. And the way that we can concatenate is similarly how we did here. If you have 2 strings, this plus operator becomes concatenate. So I could take the string of both of these. So if these were 5 and 7, this would be the string 5, the string 7. Add them together, that would be the string 57. And then I'd want to make it an int again, so that when it gets fed back in, the number's still an integer. And if we were to do that on the example data, we get 11,383, which is the result here. And if I was to run it on the actual data, okay, so no, in fact, everything is working. It just takes a little bit of time to run. And one way just to see that running is to enumerate these reports and give us an index, and do something like index of the length of that, and that'll just give us a running total. It'll slow down a little bit from this. It's not massively quick. I think it'll take about 30 seconds here. I'll just let that run through. You can see here there's 850 to check through, and it's just going to check through each one of those. There might be faster ways to do this. I think the method itself is sound, but there might be better ways to do the individual operations, or to generate all these ternary numbers, all these equations and things like that. But I think generally the method's sound, so we'll just let this run, and then we'll check the check what it outputs against what's on the website. Okay, and the program's finished here, and it gives us an output here ending in 829, and that's the answer there. So it ran in about, I think it was about 40 seconds ish. I could run a timer on it, but yeah, so that's the answer for part 2 of day 7. If you did like, please remember to like the video and leave a comment. Subscribe for all the other days. I plan to make a video for each of the days puzzles. It might not come out on the day of the puzzle, but I'll try to get them up as quick as possible. So great, and I'll see you for day number 8.